next speaker is Xuezhou Tang.
Xuezhou
Tang, and joint work with Zheng, and boosting multi-neural convex relaxation for neural network verification.
Yeah. So let's begin. Good days, ladies and gentlemen. I'm Xuezhou Tang from Shenzhen University, and I'm also the author of the Boosting Multi-Neural Convex Relaxation for Neural Network Verification. And the other two authors are Zheng and Jiaxiang Liu. Both of them come from Shenzhen University. In our practical life, because of the weak interpretability of the deep neural networks, also called as the DNNs, its inputs are always easily perturbated by some perturbation in nature or the human beings, and such perturbation cannot be detected easily by human beings. And then the perturbated input will be sent to the DNN and get the wrong result with some wrong classified result. For example, there is a picture whose original label is an owl. It's an owl, and it will be perturbated by the perturbation delta. Then for human, it's also an owl, but for the deep neural networks, its output may bring the incorrect result as the grass label, for example, grass or others except for the owl. In this situation, we consider that the DNNs is not safe for the original input under this perturbation. But the current testing technicals cannot guarantee the safety for the DNNs, so the verification for DNNs is proposed. It aims to answer the question whether the output of the DNN will satisfy some properties under the perturbation delta. For this example, the property is that the output of the DNN is the same as the original label of the input. Here's the perturbation domain of the input, which is consisted of the perturbated input, and we marked it as theta. The theta is a kind of p number whose radius is delta, and it is a convex domain. For testing technologies, they just select some samples from this perturbation domain and test their corresponding outputs, so they cannot guarantee the safety for DNNs. Compared with it, the verification for DNNs try to verify any perturbated inputs from the perturbation domain and answer the question about whether the output of the DNN will satisfy the properties. And if the property is satisfied for all the perturbated inputs, the DNN is regarded as being safe for this input under the certain perturbation. Firstly, let us describe the process of DNN briefly. For the one layer in DNN, there is an input vector which will be multiplied by the weight vector, and the multiplied result will be added to the Bayes value. The result is called as the activation input, which will be inputted into the activation functions, maybe ReLU function or sigmoids or any other functions you like. Then it will get the answers named as the activation output. The activation output will be the input for the next layer. For example, there is input vector x consisted of x1, x2, and x3, which is three-dimensional. Then it is multiplied by the three-dimensional weight vector w1 consisted of w11, 12, and 13, marked as the red line in slide. Then it is added to the bias value b1, then get the activation input z hat 1. The z hat 1 will be calculated through the activation function and get the activation output z1. Then the z1 will be the next input for the next layer. To answer the question whether the outputs will satisfy some perturbations, we should discuss the relation between the input and output for the DNN. But it is hard for us to describe such relation because it is non-linear relation. It is hard for us to discuss. So, to discuss such relation, the single neural relaxations are proposed. It can transfer the non-linear relation between the input and output to a linear one. The nonlinear relation mainly caused by the nonlinear activation functions like ReLU or sigmoid. In the slide, the red line marked is the ReLU function. The single neural relaxations methods use some linear constraints over approximated the nonlinear activation functions to transfer the relation from nonlinear to the linear. Such as for ReLU functions, some methods use the following grid shapes to transfer the relation. The grid shapes, we can say that are consisted of some linear constraints or linear relaxations. So we constrain the nonlinear activation function to some linear constraints, and maybe we can use SMT solver or LP solver. LP solver is a linear program solver. The nonlinear relation is transferred to be the linear one. We can notice that the single neural relaxations are discussing the relaxations between the activation input x1 and the activation input output y1 of just a single activation neural. For example, y1 just to x1 and xn just to yn and so on. In other words, y1 is constrained by the relaxations only between x1 and y1. That is proved that the single neural relaxations may face some convex relaxation barrier which limits its precision. To overcome this barrier, the multi-neural relaxations are proposed. The multi-neural relaxations discuss the activation inputs and the activation outputs among K neurals. The K means the relaxations discussed among K neurals, and K is not less than 2. The multi-neural relaxations methods will generate some 2K dimensional relaxations based on the groups of K neurals. For example, when K equals to 2, the multi-neural relaxations will generate a 4-dimensional multi-neural relaxations R, X1, X2, Y1, and Y2 based on the group X1 and X2. So Y1 and Y2 are constrained by the relaxations, which is tighter than the one from the single neural relaxations. And the experiments shows that the multi-neural relaxations can overcome the barrier from the single one. It's ideal to compute the relaxations of all possible groups of k-neurals, K is mentioned before, but it is impractical because of the huge computations, which is 2k dimensional. So there are questions about which and how many groups should be selected for the generation of multi-neural relaxations. The state-of-the-art like K-poly and Prima use static strategy with hyperparameters empirically to select the groups. But such static strategy will make the multi-neural relaxations methods perform differently while facing different verification problems. For example, for DNNA, maybe the static strategy will make the methods perform just so-so, but for DNNB, maybe it will perform well. Here's the static selection strategy workflow. It will firstly divide the neurals in one layer into several parts, and then in each of the parts, it will generate the groups of k-neurals. K is the relaxations discussed among k-neurals. Then the selected groups are sent to the SBLM algorithms for their multi-neural relaxations. The SBLM algorithms is split bound and lift methods, which is used to generate the multi-neural relaxations. It will firstly generate the k-dimensional relaxations of activation inputs among k-neurals. And then it will further generate the 2k-dimensional generations, which is the final multi-neural relaxations. For example, when k equals to 2, and we assume that the neurals in one, they are divided into two parts. They are Vi to Vi minus 1 to V1 and Vi to Vk. Then for parts V1 to Vi minus 1 and Vi to Vk, the strategy will generate the groups of 2 and send them to the SBLM for the multi-neural relaxations. In other words, the V1 cannot be grouped with Vi or Vk, or we can see that any neural in groups in parts V1 to Vi minus 1 cannot be grouped with any neural among Vi to Vk. That's a situation that maybe the group V1 and Vi may contribute a lot for the whole relaxations, but it is eliminated by the static selection strategy. So to overcome this problem, we propose a kind of dynamic selection strategy named FaGMR, based on the following observation. We observe that there may exist some relaxations from groups implied by the relaxations from other groups. And such relaxations are regarded as the redundant relaxations. For example, when we are computing the intersection of several sets of relaxations for the reachable set in the DNN, and the relaxations are C1, C2, and C3. We can see that the C1 are implied by the intersection of C2 and C3, and the intersection of C2 and C3 is marked as the red part in the slide. The C1 concludes the red part, so the C1 are implied by it. And C1 then are regarded as the redundant relaxations. Such redundant relaxations always have bigger volume in space, and the relaxations generated by SBLM are all convex. So we can compute its volume and select the groups based on these volumes. But it's also impractical for us to compute the volumes of relaxations from all possible groups of K, because it's equals to computations of the relaxations of all possible groups. So we turn to over and under approximated volumes and use these approximated ones to guide us select the groups for multi-neural relaxations method. It's the workflow of our dynamic selection FaGMR. The FaGMR firstly will compute the over and under approximated volumes of the relaxations from all possible groups of K. Then, based on these approximated volumes, our group selection strategy will select the groups with very small over-approximated volumes and eliminate the groups with very big under-approximated volumes. Then the selected groups are sent to the SBLM for the generation of corresponding multi-neural relaxations, which is 2K dimensional. And we can notice that we use the K-dimensional computation to substitute for the 2K dimensional computation. The over and under approximation are based on the approximation functions from vectors, especially for the under approximation one. And we improve the over approximation from vectors by utilizing the K-dimensional relaxations P, capital P, which is used in the SBLM. We mentioned before that the SBLM will first generate a K-dimensional relaxations among the activation inputs of K neurons. So that is capital P. And the volume of capital P can be exactly computed by off-the-shelf volume tools like Xuezhou, because P is also a convex hole. We can see that our over approximation is tighter than the one from vectors because we consider the relaxations of activation inputs from K neurons, especially in the scenario of multi-neural relaxations computation. And we use these over and under approximated volumes, which has K-dimensional computation to reduce the 2K dimensional computations from those redundant or unnecessary relaxations. And you can find more detailed and proofs in the section 3.2 in our FaGMR paper. These are the experiments of our FaGMR paper, and we focus on the MNIST and the CIFAR-10 data sets. They are data sets for the networks with the classified task. And the parameter K equals to 3, which is suggested in the primer's paper, and it performs best in the experiments of the primer. There are 3 verifies concluded in our experiments. They are primer or primer parallel and FaGMR. FaGMR will compute all the relaxations from all possible groups of K. And it will make a lot of out-of-memory cases. Then the FaGMR parallel is the static selection strategy used in FaGMR. And we use the same parameters in FaGMR parallel, which are the same as the ones in FaGMR. Finally, the FaGMR is our dynamic selection strategy. We can see that according to the table, except for the out-of-memory cases, the runtime on average of FaGMR is less than the ones from other two, with negligible precision showed by the verified cases in the third line. And the groups generated from FaGMR are also less than the ones from other two. That's because our dynamic selection strategy will reduce some redundant relaxations and their groups according to the approximated volumes. We can see that the reason of the improvements of the FaGMR mainly comes from the reduced groups. And we notice that especially on the MNIST CIFAR big networks, the runtime on average of FaGMR is more than the one of FaGMR parallel. That's because there are some out-of-memory cases happened in FaGMR parallel due to the huge computations. Maybe the FaGMR parallel use the static strategy will not select enough groups, and too many groups means too many relaxations should be dealt with, and it will cause the out-of-memory issues. The out-of-memory issues are not recorded in our experiments, and such cases need a lot of runtime. So that's the reason why the runtime of FaGMR is more than the FaGMR parallel in this experiment, because the out-of-memory cases are not recorded in FaGMR parallel. To further analyze the improvement of our FaGMR, we divide the runtime, the runtime into three parts. They are TGR, TCG, and TLP. The TGR is a time for neural grouping, and the TCG is a time for multi-neural relaxations generation. The TLP is a time for LP solving. LP solving is used by the linear program solvers. We can see that the TGR of FaGMR is more than the ones from the other two. That's because during the time for neural grouping, our FaGMR showed over and under approximated the volumes of relaxations for all possible groups. And the FaGMR should also select the groups according to least approximated ones. But it brings a lot improvements on both of the time for multi-neural relaxations generation and the time for LP solving. That's because our FaGMR will reduce the groups based on the volumes, and as a result, when during the time for multi-neural relaxations generation, the groups should be dealt with by SBLM are reduced. And also, the relaxations should be dealt with by the LP solver are also reduced. So that's the reason why the increased TGR can bring the huge improvements for the TCG and the TLP, and the total runtime of FaGMR will be less than the times from the other two. In conclusion, we propose a kind of dynamic selection strategy named FaGMR for the multi-neural relaxation methods, and its key idea is to over and under approximate the volumes of relaxations from all possible groups of K-neurons. And our selection strategy will select the groups with very small over-approximated volumes and then eliminate the groups with very big under-approximated volumes. So the groups are reduced and the runtime is less than the static strategy with negligible precision. The experiments shows that our FaGMR is effective on runtime and have the computative precisions. Thanks for your listening, and it's time for question and answering.
Thank you. Let's thank the speaker. Other questions? Any question on the relaxation? Relaxed question? No? I have a relaxed question. Where your system fails, your approximation fail. I mean, where you lose precision in such a way that you cannot prove what you want to prove. I mean, there is an approximation in your method, right?
Sorry, can you repeat?
Yeah, there is an approximation in your method. You have over and under approximate. Where it fails, I mean, what are the conditions, the input or the system where this may fail? How can I hack your system?
How can you hack? Hack. Yeah.
How can I
attack?
Break your system?
Yeah, I know attack means.
Yeah.
Yeah, I know. Thank you. How can I attack my system?
Yeah.
Maybe. Oh, yeah. I have an idea. This is according to our detailed selection strategy. Yeah, like this. Maybe the attacker can. Let us describe the selection strategy more detailed. Firstly, our selection strategy is compiled. We return a set of groups named G, capital G, and when there is a group candidate comes to G, and the candidate want to be selected, then we should compare the candidates over and under approximation volumes with the maxima under approximated volumes and the minima over approximated volumes among all the groups from G. So the interval of the groups of the volumes from the groups is the key for the actor to hack our system.
Wow.
If you because we will select the groups with very small over approximated volumes and eliminate the one with very big under approximated volumes. If the hacker make the interval of the volumes too approached with each other, maybe our system can be more easily to be hacked.
Okay. Thank you very much. Wonderful answer. Other questions? No? Okay. Thanks, speaker.
Yeah. Thank you.